Yeah, so let me then directly dive into with lecture. So what were we doing till now? We were been looking at the sorting algorithm. Some of them that you have already seen in your maybe in your programming class or something like that, and some of them that you might not have seen till now. So to kind of recap, so where were we? So we had seen things like insertion sort, bubble sort. So we kind of rushed over them, but if you have any doubts, I will be happy to go over them. Insertion sort, bubble sort, selection sort. So these three things we kind of saw, and basically all of them had a runtime of the worst case runtime of order n squared, right? And in some cases the best case was order n, in a couple of them it was order n squared. But yeah, so basically this was the case, and I kind of did not prove it, but you kind of left to use it to kind of confirm that the average case for all of them is also order n squared, right? So this is what we had, but the good thing was that the space, we don't need any extra space. So space was basically order one, or maybe we can just write it as order log n, whatever. So it's basically, there's no extra space. I just need space to store some indices or one value or something like that. But we don't need a more than that. Anything.
Sir?
Yeah.
Sir, could you just explain or could you just demonstrate how to tackle this problem of finding the average case runtime for any
right?
one of them?
I will show it to you just today only, but not on this three problem.
Okay.
I will do it on another problem. Mind you, these three problems, average case runtime is actually very easy to calculate, because all you have to prove is that the upper bound is n square, right? So all you need to prove is that the average case is n square. And one way of proving is that for at least half the possible set of inputs, the algorithm will run for order n square steps.
Okay.
Right, and that would give you a, I mean, kind of a, so yeah, it will be a theta n square. Because both of them are theta n square, basically meaning you can prove that there is a lower bound of n square, and since there is automatically an upper bound of n square, so you get this answer. Okay. So now after this, we saw this thing of merge sort. Now we will be going over this merge sort maybe once more, just to kind of recap whatever we were doing. And the basic idea was that, okay, if you give you a big array A to sort of the A1 to AN, what you do is that you split it up in the middle. So the first half, so this is basically the n over 2 kind of bound, so maybe floor or something like that. So that is fine. Then the first half is B, second half is C, and the basic idea is that, so merge sort of A is basically what you do. Okay, so let me just kind of write down here what you do. So you first use merge sort recursively to sort the first half. You use merge sort recursively to sort the second half. And you then, so let's call just for the maybe with the abuse of notation, let's say that after sorting I have got this B, after sorting I have got the C. So now B and C at this point means the sorted parts. So this is this first one, which is this first half sorted, second half sorted, say. And then what you do is that you merge these two sorted lists. Now, and that's it. Okay, of course, that is not the it. There are a couple of things that we have not written. Number one is what is the pseudocode of merge. Now, okay, so merge was something, that basic idea was that, I mean, you go by one. So if I want to merge B and C, the main idea is that, okay, here I have a B is sorted, C that is sorted, and you basically maintain a pointer, and you maintain another thing which is a merged one, and you, whenever you are at any point of time, you are looking at 2 points, one from B, one from C, whichever is smaller, you just put it here and move the thing to the next one. And so I went over it last time. I'm not going to go over it too much here, but the basic idea is that you kind of go over all the points in B and point of C once, right? As so that is the most important thing to note, that the smart sorts, that takes an order n, or order, maybe I should not say n. Okay, so order B plus C amount of time. So for merging these two sorted list, I need order B plus C amount of time. Right. So also in this merge sort here, I have not given the base cases, but you have to put the base cases. But that I'm kind of avoiding for now. Like for example, if the total length of A is just 2, then you don't have to go into this kind of merging, breaking up into 2 parts and so on. You can just apply a brute force and get it done. Right. So, but those is other than the base cases, this is what the merge sort does. Now, what is the time complexity of this merge sort? Okay, so if A is of size n, and so Tn is the time taken, a number of steps taken by for merging A. So this is obtained by first merging B, merge sorting B. Now B is of the size n over 2, so this should be taking T of n over 2. So here I'm kind of didn't write it. So Tn is the, say, worst case runtime for merge sorting n length array. So Tn is actually less than or equal to T of n by 2. Actually, it will be so one of them will be yeah, there will be floor and ceiling kind of stuff like that. So this is P is n by 2, C is also n by 2. So yeah, so maybe I should, if I kind of write it very precisely, it will be T of, say, n by 2 plus T of n minus n by 2 plus, now this merging, right? Now B is of size something, C is of size something, but I know that B plus C is of size n. And by this argument, I know that merging of B and C takes order n. So this is order n. And if you just basically solve this equation, you will get that T of n is order n log n. So is this clear to all of you?
Yes, yes, sir.
Okay. So good. So so there are certain things to note here, and that is something very important. Maybe it is like obvious from here, but why is this n log n coming up? Right? It is mostly because of this thing, that I'm sorting into, if this one was smaller than order n, if I could have somehow merged in less than order n, then I would have been good. I'm in good shape, right? So excellent. Right. okay, that is one thing. The other thing is that, I mean, is it something, can I do something else that will reduce this n log n completely? Can I beat the n log n bound? So there are three things that are coming out here, right? So namely, or rather two things maybe, is n log n or order n log n the best we can do? Right? Number two, okay. Yeah, so here we have the another thing that is important here is that in merge sort, we have used space. We have used an extra space here, right? So space that I've used, so it's the extra space is order n. So do we need this extra space? Now there are other options. Like I kind of talked about things like uh, that mm, whether this is uh, the in-place sorting or whether it is stable sorting. So these are the questions that, of course, we have to ask, right? Is merge sort stable sorting? So then maybe, so let me try to, if you guys have understood this merge sort thing, let me try to explain these three questions in today's lecture. Okay, so we have got n log n. N log n is, of course, much better than n square that was there previously. Excellent. But can we do better? Can we remove this space? And maybe the marks. Okay, maybe the last question I will leave it for you to as an exercise. You can go and think about it. But let me try to understand, address the first two questions. Okay. So before that, let me say that let me say that I have a crazy idea. Okay. That's the issue about this merging was that I don't know how these two things are, I mean, the comparison between them, right? And that is why I have to go over all of these things and all of these things. So what happens if I can somehow ensure that every element of B is smaller than every element of C? If I can somehow ensure every element of B is smaller than every element of C, then if I can somehow get this thing sorted and give this C sorted, then I can just put one over the other and done. Right? So this is a very natural way of going about it. And this is what is called, in fact, something called a quicksort. Okay, so basically what it does, so I have been given what do I have been given? I have been given A, so I mean A1 to AN, right? An array of n elements. Now what do? I let pivot. I have assigned the first element as the pivot. A1. I take that one as the pivot, and then what I do is that I partition A into two sets or two arrays, or B and C, such that, so basically what I get, so maybe I will just write it in a kind of a nice way. So this is the pivot. Okay, so the pivot is somewhere in the middle. Okay, so this is the pivot element is sitting over there. Now everything here is less than or equal to the pivot, and everything here is more than the pivot. So this is my B and this is my C. So if I can basically partition or kind of write A, kind of take look at all the elements of A, put the elements, right? Put the elements of A that are less than the pivot in B, and put the elements of A that are more than the pivot in C, then all I need to do is that I need to just then, using the same kind of a technique, right? Same kind of a the recursive call, I can just quicksort B and quicksort C. And what will I get? That this part, first part will be, because of the quicksort B, the first part will be sorted, and because of the quicksort C, the second part will be sorted, and that's it. So this is another algorithm called quicksort algorithm.
Sir,
Yeah.
do we pick this pivot randomly?
Right now, let's not do it. Okay.
Okay,
Let's say that we just take the first element of the pivot.
Sir,
Yeah.
is a pivot and different component of A, or is it with B?
So you can think of it, pivot is just separately, because we know that the pivot I don't need to support, right?
Yes, sir.
So we can, because pivot is something that is always more than or equal to all the elements in B, right? So B plus C is say n minus 1,
Okay, sir.
right? I mean, even if you put it with B, that's also not a problem as such, but yeah, either of them is fine. Now, can somebody nice advantage of this thing?
So could you repeat?
Can somebody see some advantage of this particular algorithm?
So this solves the problem of merging, because we
Solve the
get
problem
the
of merging, that is true. I don't have to merge, and so
answer. So the order n step in the previous step just becomes a constant time.
right. So order n steps becomes constant time. That is also true. So there's no merging at all, right? Okay, so let's see. So the time complexity. Okay, so now that is a bit of a tricky thing. Okay, let me use a different color here. So what is the time complexity? So again, if I define this Tn as I had defined earlier, this is the worst case runtime to sort any algorithm. So what is this? This would be this part. How will you go do this part? How will you partition A into two arrays? You don't have partition into two arrays. You can partition. I mean, you can push the pivot up, right? Basically, you say that, oh, okay, as soon as you see an element that is, I mean, that is bigger than the pivot, you keep it on the left, and otherwise you keep it on the right. Now, I am not going to prove it to you, but this one, I want you guys to write a code, pseudo code that does this thing. Okay, and I want you to do it in order n steps. Okay, so you can do it. Yeah.
So we have a pivot, and basically we have to separate the set in two parts, thus by comparison with all the points.
Right.
So it will take n. I mean,
it will take n, but writing a pseudocode there properly, formally, if you have not done it already, have you done
okay.
this one, by the way, in your this programming course?
No, sir.
No.
We haven't done Quicksort.
You have not done Quicksort. But okay, so you just write this code. Okay, this code you have to handle this ij carefully. That's all I'm saying. Okay. Yes, order n is required, and you can do it in order n. Okay. So, anyways, you do it. So this is your exercise in some sense.
So the whole quicksort, or just the?
No, just this one.
Okay.
Just the partition.
Sir,
Okay.
so actually, it's illusionary that we won't have that order n step, because this step would then require at least order and time complexity.
Right. So this will, it will anyway. So the merging that was done, it has been pushed in the beginning.
Right.
Right. So earlier we were like breaking up into two halves. That was done in order one step in merge sort, right? Here, that is not the case. The breaking up into two halves is taking order n. But
Okay.
again, merging is not taking time.
So, sir, so in this case, I mean, for Quicksort, that big O of n won't be there, right? On the right hand side.
In which case? So the
I mean,
thing
in
that
Quicksort, so Tn will be just 2 times
Will
Tn by 2.
okay, so it will be 2 times what?
Tn by 2.
Tn
If we
by
choose
2. Okay, that's what
consider
you are
most
saying.
part.
But what happened
And
to this one? Partition.
oh, right.
But earlier the merging was required n times, right?
Yes.
But the breaking up was not taking n times. Here the merging is not taking n times, but the breaking up is taking n times. So it will be kind of order n plus something. Okay, so
Sir,
we have not
sir-
made much progress as such.
Sir, technically it should be T of A plus T of B instead of 2 times T
Very
of n
good
by 2.
point. Somebody has pointed out some very nice thing. Actually, it is not n by 2. It is T of B plus T of C. Not 2, there's no 2 here. Right? Now, this is also something bad news for us. Okay. Why? Because what happens if the pivot is the smallest one? Whatever the pivot is, I mean, we picked up the first element and our luck is so happens that pivot is the smallest one. Then what happens? What is B? What is C?
Yes, sir. So in the so the B would be n minus 2 and C would be 1. Oh, sorry.
Or
B
whatever,
would
yeah.
be
Otherwise,
yeah.
right. So B will be 0 and C will be 1. So in the worst case, this will become T of n will be order n plus T of n minus 1, right?
Yes, sir.
Which
Yes,
is n squared.
would be n square.
And if I going like this, you will see that T of n equals to n squared. Okay, so we have actually not done any progress. So we started from merge sort and we tried to make our life better. But at the end of the day, we have managed to goof up even worse.
And sir, ironically, that's the case where the array is already sorted. That is when it takes the most time.
And that is the case when the array is already sorted. Right. So it's a very bad thing. Okay, this is the worst case. But still, is there anything for which we would like to kind of look at the Quicksort in a bit more depth? Do you see any other aspect of Quicksort that is useful for us?
Sir, it is taking up no extra space.
That's a good point. It is taking up no extra space. Because this whole thing, this is something that I've told you that do the exercise in order n, you should prove it that you can do it in situ, meaning you don't use any space. You can do this whole operation without producing any extra array space. And once you kind of produce it in any extra array space, then Quicksort of B, you can do this first half, Quicksort of C, you can do it in second half. And you can see that everything is done at that place. So Quicksort, unlike merge sort, is not taking any extra space. Okay.
So I have a minor doubt.
Yeah.
In merge sort,
Yeah.
if we work with arrays, then we know we have to create another one. But if we were working with linked lists, would that still take extra space?
Yeah,
or
yeah.
can we just not?
That will
Can we
still
not
take
just?
more extra space. Okay, there is a version of merge sort where you don't need extra space. I'm not going into that. It is called in place merge sort. But
Okay.
that's a much more, I mean, that's a bit more sophisticated. That's a generalization of something like that. Okay, but normal merge sort is this. in which you will need a margin fee. You'll need extra space. Okay, so good. So here we are. We started from something which is order n squared and constant space. We went to order n log n and n space. And now we're back to n square and order 1 space. Right? But let's see here. So this is the worst case, right? Do you think this can happen regularly? I mean, if somebody is not there just to kind of make fun of us or really trying to be an adversary to us. So for a random data, in fact, for a random input, can this happen always? Can it be that every time I pick a pivot, that pivot is the worst, is the lowest or the maximum, highest? So
No.
note that even if this pivot was somewhere in the middle, okay, so even if somehow the pivot was splitting it up into somewhere, so it's like order n plus maybe t 2n by 3 plus tn by 3, somewhere 1/3, 2/3 kind of split. Even then, this would have given me n log n. So this was a, so even if, I mean, I don't need the pivot to split it perfectly in the middle. But as long as it is somewhere in the middle, which has enough fraction in the both halves, the runtime would be n log n. Okay. So while it is true that the worst case setting is this, we don't expect that this to happen always. Only for certain inputs, this will happen. So in short, now we are kind of would like to ask this following question. What is the average case runtime of Quicksort? Now, what does average case runtime mean? So average case runtime is that, so there are how many possible inputs? There are n factorial different inputs, assuming that all the, I mean, if I give you an array A, right, A1 to An, and let's assume that all of them are disjoint, distinct, then there are n factorial different possible ways of permuting it, right? So there are n factorial different inputs. So for any particular input, compute the speed or time complexity taken by Quicksort. Okay, so for a particular order, so say, so let me call this n factor. So for a particular permutation in Sn, right? So it's a permutation over this n thing. I can define that T pi is the time taken by the Quicksort. So the average case runtime of Quicksort, this is sum over Tp whole by n. Is this fine?
Yes, sir.
So since you guys
Sir,
are, yeah, go ahead.
can you repeat in what you said in the last 2 minutes. I have some connection problems.
Okay. So I was just defining what is average case quicksort, average case runtime of quicksort.
Yes, sir.
So if I have this input A1 to AN, so note that we are only concerned about the ordering of this element, right?
Yes, sir.
We are not concerned about whether A1 is what is the value of A1. I'm not concerned about that. I'm concerned about how is A1 related to A2 kind of stuff.
Yes, sir.
There are n factorial different orderings,
Yes, sir.
right? So basically, I can say that they can take a permutation from Sn, and any permutation from Sn gives me an ordering of A1 to An.
Right, sir.
And for that permutation, if that is the input, if the input is given according to that, then the time taken by the quicksort, I will define it as P of sigma.
Yes, sir.
Now, the average case runtime of quicksort is nothing but this much. Summation of P of sigma by n factorial.
Thank you, sir.
Right? So that's it. Now, since you guys have from C, you can very well see that this is same as, right, expected value of P of sigma when sigma is drawn from T factorial uniformly, right?
Yes, sir.
Okay. So this is what you have to calculate. If we can calculate it, then we are done. Okay. Now, let me say that this one, I'm now writing something which is kind of same as this thing. So what happens if I consider, so let's go back to the quicksort. This is where somebody had pointed out that I have picked up a pivot which is equals to A1, the first element. What happens if I don't pick it with A1, but with pick I, so I will say that pick I uniformly from 1 to n, pivot equals to AI. Okay. Now this is a different kind of algorithm. Why? This algorithm has a randomization inbuilt in it. Okay. These are called randomized algorithms. And we can first ask about the expected runtime of the randomized quicksort. Okay, so is the expected runtime of the randomized quicksort? I hope that it makes sense to you guys, right?
Sir, are these two algorithms not absolutely equivalent to each
These
other?
algorithms are not equal, but what you are saying is kind of correct that this object and this object, they are same.
Right.
Okay. The algorithms are not. In one of them is a deterministic algorithm, one of them is a randomized algorithm.
Okay. Okay. Sir, so the major difference would lie in the sampling design of the array.
Right. So it's like if in one of them, if I give you the if I give you a if it is a non-deterministic, it's a deterministic algorithm with the A1, then
Right.
an adversary can necessarily make my algorithm run badly.
Right. Right.
If it is this, then whatever the algorithm adversary gives doesn't matter. It's all in the probability here. It's
Right.
all in my random coin tosses. If my random coin tosses are bad, then I'm not going to do well. Okay. But
Okay.
basically the same thing will happen. So these two things you can take it, if you are not convinced by, you can take it also as an exercise. Convince yourself that these two objects are identical. These two values are identical.
So actually, the first quantity is also calculated based on the assumption that whatever input we're getting randomly, uniformly randomly.
It's the average, right? It's the average, plain simple arithmetic average, arithmetic mean. And arithmetic mean is exactly by taking uniform.
Oh, okay, right. So there's no probability involved in
There's
this.
no probability involved. I'm just written it in this way. That's it.
Okay, right.
But that is just plain arithmetic mean. Okay, so yeah, in one algorithm it is. So let me give you guys a couple of minutes. Why don't you guys try to estimate the expected runtime of this quicksort, randomized quicksort. Okay, and then I will come back and try to hear what are your ideas, and accordingly we go about it. Okay. So why don't you guys minutes to think about it? How can you proceed if this is a question that is asked to you guys? Right, here is an object, you have done some stuff, and now all I'm asking is to calculate the expectation, something that you have done n number of times in your ISI courses, right? Compute the expectation. Yeah. If you have some ideas, then either you can raise your hands or send something in the chat.
Sir,
Hello, any idea? Hello. Hello.
Yes, sir, we can hear
Yes,
you.
Yeah, any idea from any of you? So let's see. So how will you go about it? Okay. So here is this A1 to AN, right? Now I am picking up at random a pivot, an AI. That is my pivot, right? So this one can be any one of them. So with probability 1 by n, it can be anything. So any AJ can be there with probability 1 by n. So let's say that that the actual ordering of them is say A1 to AN. Okay, this is the actual ordering. Means A1 is less than equals to A, less than equal to AN. So I'm picking up AI randomly. Basically, I'm picking up an AJ somewhere here randomly, right? And splitting this whole set into two halves, right? So if I pick this one as a pivot, so basically if AI is actually equals to AJ, then what is my step that happens? Then P of n, of course, there is an order n, which is the initial part, but the other parts, what happens? How are the two parts? If it is this case,
So this is T of j minus 1 plus T of n minus j.
this T of j minus 1 plus T of
T of n minus j.
n minus j, right?
Right.
Now this happens with probability 1/3, sorry, 1 by n,
Right.
right? Now j can be any one of them.
Yes.
So this is nothing but summation over this quantity j equals to 1 to n, and I have to of course normalize it, is 1 by n.
So this is
here,
expectation, right?
yes, the expected value of t.
Okay. So essentially what we are doing is, if you're saying let expectation of T of n be something like lambda n.
Something like that, right? So maybe let me say Tn itself is the expected, I mean. Yeah, so Tn is actually equal to the expected, is the expected. So Tn is the expected runtime of Quicksort. On an array of size n. Then this is what is happening, right? So I have Tn. It of course does this initial one is kind of no problem at all. And then what happens next? Of course, there are recursive calls, no doubt about that. But recursive calls of what size? For every 1 by n probability, it can be Tj minus 1 and Tn minus j and so on.
So this is the step where you essentially conditioning on the size of B, right? And so size of B.
I'm conditionally conditioning on size of B. Yeah.
So this is just actually it's just the tower property that we're using.
Yeah, I mean,
Where
you
we
can,
are
yeah,
using the conditional expectation.
right.
Yeah.
I mean, this is not just, I mean, just the J would have been the conditional expectation. And the summation of J, yeah. So I'm using conditional expectation to calculate the whole thing.
Right.
Right.
Yes.
Now this is kind of easy to see that this is basically two sums, which basically ends up being the same thing, right? P of j minus 1, j equals 1 to n is same as P of n minus j, j equals 1 to n. Correct?
Yes.
Yes.
Sorry. So this is P of n 2 by n summation of P of I equals to 1 to n, or maybe 0 to n minus 1, whatever, something of this. Don't worry about whatever it is. Now, you can do the calculations yourself.
Sir,
Yeah, go ahead.
what will be the base case? I mean, P of 0.
Yeah, so that is something that you can fix, right? So that is, I have not told even in this Quicksort as well as in the merge sort. So you can think of the T of 1 is 1, or T of 1 is 0, or T of 2 is 1. Right?
Yes, sir.
I mean, that is just a, I mean, you can either stop when the size of this array becomes 1 or size of the array becomes 2. Right? So that you can, that I have not written the base case for here. So you have to write the base case. Either of them is fine. Okay. And maybe I will leave this one also as an exercise for you guys. That once you have this one, how can you solve it? I mean, the standard way that I can say is that you can convert this summation to an integral.
Sir?
Yeah.
Is not the sum is also equal to 1 to n minus 1?
I think it will be 1 to n. That's true. Or it would be
0 to n minus.
It will be 0 to n. Yeah, so you can think of the 0 is 0, so it's like T of 1 to n minus 1 actually.
Okay. So maybe we can use induction.
You can use
Where the-
induction, or you can
hypothesis-
actually simply replace this one by an integration. Okay. So this is nothing but integration of tx, or this is x equals to 1 to n minus 1.
And then use a differential equation.
Yeah, you don't have to do all of that if you just do the integration, because it's just a kind of a simple thing. You
Okay.
can actually prove what happens there. You can apply and kind of guess and all those things. So basically, you can end up proving that T of n equals to. So this I'm leaving it to you. Go and prove it. T of n equals to n log n. In fact, I can write it very much more simple. If this n is, I forget this constant. Okay, if the constant is 1, and this is actually equals to 2 n log. Okay, so this is one way of calculating the average case runtime of the quicksort, or the randomized thing of the quicksort. There's another way of doing it. So let me give you that way also. That's another very nice way.
Sir, to be clear,
Yeah.
here we're setting the pivot as AI, where I is chosen randomly.
Yes.
And then we have to still find that exact point from AI where the first numbers are lesser than the pivot and the second.
Yes, that we have to do. Because if you don't do that, how will you separate them into this kind of this chunk? So once we have the pivot, you have to split up this A into these 3 parts: less than pivot, pivot, and greater than pivot.
But that pivot will be different from AI.
No, this is the AI.
But
This is the AI. I mean,
So-
this will be different from AI, meaning
Okay, so the process is the pivot is at AI.
the X. You can say this is the X. So if AI is value is X, then this X pivot is the X.
And that could be random uniformly.
Yeah. So your pivot is X, where X equals to AI. Basically.
The pivot started at A1 and then we found the actual pivot at some.
Pivot doesn't start
So-
at A1.
Yes, sir. So there are two things. First thing that, so randomize quicksort and simple quicksort. So I guess that's the
Yes.
confusion.
Yeah, the simple quicksort pivot just picks A1. Pivot is the value stored at the first location. Okay. So in the case of the standard quicksort. In the case of the randomized quicksort, pivot is a number. Okay, pivot is not an I. Pivot is a number with a value. Pivot is a value that is stored in one of this A1 to AN. Okay. So in the randomized one, you pick an I uniformly at random. Whatever this value is, say if AI at that point stores 100, then pivot is 100. From the next rest of it, pivot is 100. That's it. Pivot is not changing any longer. So once pivot is 100, then you find out all the elements in A which are less than the 100, whose values is less than the 100, and all the elements whose values are more than the 100. And you partition this A into these three things.
So more than 100. I mean,
No,
sorry. Okay, sorry. I mean,
more than
sorry.
100.
AI is equal to 100.
AI equals to 100. So pivot is not I. Pivot is the value stored in AI.
Sir,
Yeah.
just
Is
to
it
be
clear or
clear,
are you confused? Yeah.
yes, sir, I was saying that this order n term is coming because of we are choosing the pivot on the order of n times, right?
No. So let me tell you, give you something, okay? Okay.
Yes.
Say, think of it that in your class, all of you are standing. Okay.
Yes,
You
sir.
are there, right? Now I catch all the first guy, and my job is to sort you guys up according to your height. Okay. So I catch hold the first guy I find and tell her, okay, you are the first guy. What is your height? He says, oh, my height is 5 feet 10 inches. Good. You are the pivot. What it means is that 5 feet 10 inches, anybody who is less than 5 foot 10 inches, stand in the left of him. Anybody with the right of 5 foot 10 inches, stand in the right of him. Okay.
Yes,
And
sir.
that's what the pivot is doing.
No,
While
sir,
doing so, yeah, sorry.
no, sir, you just continue. I will ask in the last.
Yeah. So it doesn't matter where the pivot was, what is the I and all those things. That person is the pivot. Okay. So in the random one, what happens is that I catch hold of a random person. Maybe the random person is standing in the last of the queue. That doesn't matter. Wherever that I find hold of a random person, bring that person out and say that, okay, what's your height? Anybody who is less than this person, stand in the left of him. Anybody in the right of this person, stand in the right of him. And this is what is done here. Okay. Now, how will I do it? Now, every person other than that person will have to go and compare with him. So, am I taller than you? Okay, I'm smaller. I'm shorter than you, so I should stand left of you. Or somebody says, "Oh, I am greater. I'm taller than you. I'll stand right of you." Right. So this sorting, so this pivot at this point is not like this is not AI. This is not I. Okay. I'm not saying that pivot is at the ith position. No. The value here is AI. So AI initially was storing some value, right?
Yes, sir.
So this value is here. So if AI equals to X, then it is X over here. That's all. Now this might be in the wherever it is, I am not interested. But all I know is that any element of A or any number in A that are less than or equal to X is here. Any element of X that are more than or equal to X is here. Okay. I mean, in the real life, we have used this partition on many times, by the way. Think of it in various cases. You kind of come up with a threshold, right? So you go and stand in a queue. And you are there, you have got a token. Okay, who has the token number 200? Anybody who has less than 200 token number stands here, the other one stand in the other side. So this is exactly what we are doing in the partition. Is this clear or it's confusing? Can it? Hello? Yeah,
Yes, sir.
Rita?
Yes, sir. I was asking that the order in term is coming because we are comparing these n elements with the pivot.
Right, exactly.
Now I understand.
Order in terms is coming because we are comparing each of those n elements with the pivot. Because every of the element needs to know, are you less than the pivot or more than the pivot?
Yes, sir.
So somebody else was asking about this initially, with the confusion about this AI and what happens there.
I was wondering, I was thinking that we are moving the pointer itself to a certain point in the array so that the BC partition is possible. We are moving the pointer itself.
I mean, we are not, I mean, there's no pointer. Yeah, I mean, we are just kind of separating them into less than equal to X and more than equal to X.
Yes, I mean, we are rearranging the array itself here, but I thought we were just moving the pointer.
We are rearranging the array. That is very crucial. So that's why if you can just sort B, that's good enough. For sort C, we are good enough. So B has all the elements of B are less than X, and all the elements of C is more than X. Okay. Is it clear?
Yes, sir.
Any other questions? Okay. So as I was saying, there's another way of computing the expected value. And this actually just now what we discussed might make yourself a bit more easy to understand. That okay, so let's say that Xij, this is the random variable indicating if okay, so says that I have this. So again, let's say this is something I don't know, okay, but let's say that this is the final ordering of this actual ordering of the stuff. Okay, so let's Xij is random variable indicating if AI and AJ are compared anywhere, anytime in the algorithm. Okay. Now, if this is the case, then the expected or how many elements are compared at the end? How many elements are compared is nothing but summation over I, summation over j, Xij, and my expected runtime is exactly this. This is expectation of right. So all I have to do is that I have to compute this particular thing. Now, good. So what is this? Let's see. When are two elements compared? Let's go back to this picture. When is an element X and Y compared?
One of them is a pivot.
When one of them is a pivot, only then there's a chance of X and Y transform being compared. But now that is for a one step, right? In the first step, let's say, okay, in the first step, I have this huge A, and I am saying, okay, what is the probability that, so maybe I should write it here, draw it. So this is the first, think of the first step, okay? So at this point, I'm writing it A. When I'm writing in the capital, mean I have no idea where these are, right? So there is, say, maybe AI, AJ is sitting here, maybe AI is sitting here. I don't know where. What is the probability that these two are compared? Note that the only time it is compared is if either this one is a pivot or this one is a pivot. Okay, this is the first round, right? Now, if they are not, and what happens if after I partition, let's say AJ, because in this side there's a pivot, maybe up, maybe AJ is smaller than AI. I have picked some pivot, and AI is less than the pivot, and AJ is more than the pivot. In that case, in the second round, is there a chance of AI and AJ being compared?
No, sir.
There is no chance, right? Once AI and AJ are in the two other sides of the pivot, I will recursively call on this and this. There's no way AI and AJ will be compared, right? But if after doing so somehow AI and AJ are in the same side, then again there is some chance of getting compared. Okay, so this is what we have understood. Now let's look at this ordering. Okay, so I have say A1. Let's say without loss of generality, let's say AI is less than AJ, and so. So it's like a game that we are playing. We are throwing a dart. The dart pointing to a pivot. Okay, so I throw a dart. Okay, so basically it's same as randomly pick a K between 1 to n. Now, okay, so that few things can happen. Number one, okay, if, so let's say this is the dart that picks K, right? If K equals to I or K equals to J, then Xij equals to 1. If K is between, okay, is not sorry, if K is between okay, I and J, maybe this is I plus 1 and J minus 1, then I know that Xij equals to 0 and it is never going to change, right? But if the K is otherwise, meaning it's not, so I mean K is strictly less than I or K is strictly more than J, then repeat this case. Right? And you play this game continuously and let's say what's the probability of, now I'm interested now in this game, what is the probability of Xij being equal to 1? Do you see this game? Why is this game coming?
Yes, sir.
Hello?
Yes, sir. Yes, sir.
Yeah.
So we just need to actually just get a cumulative of all the times we can say for sure that I and j will not be compared. So in this first iteration, we need to find the probability, and then in the subsequent iterations, we can just add up the probability in a.
Yeah, calculate it. Okay, let's see. Can you just say?
So in the first round, it is 1/3 probability that the second case happens. Because I,
First
j,
round
and
is
k
a
are,
1/3 probability the second case happens.
right, because I, j, and k are all just randomly chosen.
Why is it 1/3?
IJ I think fixed is
Yeah, fix an I and j.
Oh, okay. If you fix an ij, okay.
For a fixed I and j, what is the probability of it being 1?
So that's just n.
Use complementation.
Complement. What is the
Like in the use the case for which xij is 0 and then subtract it from 1 minus 1.
now? Why don't you think a little bit, all of you, and just try to give me an answer?
N minus j minus I divided by n. N minus j minus I whole thing divided by n.
Okay, think out it. A kind of close, but not exactly. Okay, let me give you a couple of minutes for all of you. Okay. And by the way, I don't understand why aren't the rest of you are not even interested. This is what I'm doing is purely probability. So am I kind of ready to accept that most of you are not interested in probability also?
So this is like, we are tossing a coin till we are getting ahead type of situation. So
Not exactly.
no, but we
Exactly,
we
because there is a
can
middle thing that if you fall in the second category once, then you don't toss any longer. The game closes, right?
yes, that's what I'm trying to matlab, so
Yeah.
can we calculate it like that, right?
You can think about it. Yeah, basically this. It is not exactly kind of, yeah.
So what will be the value of the random variable in the case for 3? If k equals to 1, then we can say that we can have k
But
equals
the
to I or
equal to
j.
3 means what? I don't understand.
K equals to not 3, I mean that for the third case, k less than I or k greater than j.
Exactly, that's exactly what I asked you to compute. It is not automatic, right? Because you repeat the process again. That's all.
So do we have to
If
calculate
so if
something?
k is something else, right? So k is here, right? So say this is k. Then the next round you have this part, right? But back to whole the game is played again on this half from n minus.
Okay. Right.
So do we have to condition on that or something?
Think.
So not a coin, but a 3-face die kind of thing.
Kind of.
Yeah, no, that would we have to sum that.
Okay, so let's help you. Okay, somebody told condition. Condition on what?
That's what I'm confused about.
So what about if you condition on the fact that, okay, in this round, the game stops? Then what is the probability that xij equals to 1?
2 by n.
2 by n? Are you sure?
Yes, sir.
Why?
So because K has to be either I or J. If Xij has to be 1 in this round.
But in game the middle one also. That's also the game stops. The game stops in both of them. This is the only case when they repeat game continues.
Oh, so you're asking for the probability of either the first or the second case happening.
Yeah, so say if I condition on the fact that the first or the second case happens.
Okay, okay.
So that is the case when the game stops. For a particular I and j, that game stops there, right?
Okay, right. So that probability is j minus I plus 1 divided by n.
Are you certain? It's a condition. Think about it.
So what did you ask? I mean, if the game stops,
It's
then
conditioned on the fact that the game stops in this round. Okay. I mean, I've conditioned, I've guaranteed you that you toss the coin and you have been conditioned that either of these two cases happen.
Oh, okay.
Then
So
what is the probability of this being 1?
So that's 2 by j minus I plus 1.
Exactly. So if it stops, if the game stops, meaning it is the k has to be in this range.
Right.
Right? Has to be in this range. Condition on that game stops, it has to be in this range. And only if it is this two, only then it is xij equals to 1. So conditioned on the fact, that the game stops, probability that xij equals to 1 is equals to 2 by j minus I, right? Or j minus I plus 1. This is the length, right? Number of numbers that are there is j minus I plus 1. Out of this, these are the two only things that can happen. Now think of it. Can you now say what is it? Every time you play a game, with some probability it continues. It continues. Some probability continues. But when it stops, the probability of getting 1 is this. So probability of xij equals to 1 is actually 2 by a minus I. Are you guys confused or not?
Okay, so you're saying that you're conditioning on the stopping time, and
Conditioning on the
since
stopping fact, not time. Yeah, conditioning that this is at see if we have what does the meaning game stop, right? The game has still not stopped. That means till now xij has not been put to 1 or 0.
right,
At that time xij is still not been decided.
right.
Okay? Now here I'm guaranteeing you that this is going to stop now.
Okay, right.
Right.
So another way of posing this is if we suppose t is the time that it takes for the game to stop, which is a random variable.
Right. And then you condition on that thing.
So conditioning on that, we see that this is a constant. So the unconditional probability will have to be the constant conditional probability.
Exactly. You can think of it.
Got it.
Right. So probability of xij is actually 2 by j minus 1. Okay. Now I am leaving it to you to go and calculate it. That summation of I and j 2 by j minus I plus 1. What is this one? Okay. So if you just do this whole thing, this is nothing but summation over I. Okay. So 2 times, let's see what is happens here. I have a j, right? So j equals to 1 to n. So this starts from what? 1/2, right? Then it is 1/3, and it keeps on going, and it goes up to how much? N is equals to, of course, again 1 to n, right? Equals 1 to n. So fixing I, this is equals to n minus I plus 1. Now, have you guys seen this kind of this sum? Do you guys know what the sum is?
Should the sum start from 1?
Sum doesn't start from 1. J equals to I minus, so what is J?
Both I and
Okay,
J
J
are
equals
1.
to I, right? J equals to
Yeah,
I
then-
plus 1. So J equals to I plus 1 to n.
It's a bounce.
Yeah, J equals to I plus 1 to n. I mean, I'm just doing this. Yeah, so whatever I written there is kind of wrong. I mean, I'm not wrong. I just written it as summation ij, the summation I equals to 1 to n, j equals to I plus 1 to. Right? You want to calculate xij only once, not twice. Right? So this will be 1 and this is 2. There's 2 by, I mean, yeah, there's a 2 here. Yeah. Right? So what is this quantity? Because I would say what is 1 plus 2 plus 1/3 plus 1/4 plus 1/9?
Sir, we can bound it by integral. Sure.
What is it? How much is the bound?
Log n.
This is log n, right? So basically, this is the h of n. It's called the harmonic sum, and this is basically h of n. So now you put this one here, and what you end up seeing is that this is summation of I equals to 1 to n, 2 i's of, yeah, basically it will become 2 i's of hi, which is to the calculation just 2 n. A bit less than, and you can get. Okay, so I have given you 2 different ways of measuring this quicksort. Did you guys follow this thing? I mean, this was nothing but simple calculation of probability. So what all things we have? So we have this quicksort algorithm. Okay, and the thing is that the expected runtime of randomized quicksort is, let me put it as order n log n.
Sir, could you just scroll up for a second?
Yeah. Over here.
Yes, sir. So should that be hi or?
Yeah, it will just be opposite, right? Look at this one. This is a value that goes from I equals 1 to n, right? It's h of n minus I, if you want to think of it this way. That's the same.
Yes, sir, I got it. And sir, there is a 1 in the HN expression
Yeah,
of
so it's
HN.
-1. Again, that doesn't matter. Again, that doesn't.
Yes, sir, fine. Thank you, sir.
Okay, so expected runtime of randomized quicksort is order n log n. Now, let me ask you something. So you guys have, of course, done probability. You have done. Have you gone over some of the concentration bound, like Chebyshev, Chernoff, Markov?
Yes, sir.
Yeah. So in the case of, I mean, so like for example, say if you run this algorithm, okay, to run this algorithm, then it might be somebody can say, see, you are saying that the expected runtime is n log n, but maybe for a big chunk of them, this whole algorithm is taking only order n steps. And for a big chunk of them, it is going up to something like maybe order n log square n kind of stuff, or even n square, such that the average is n log n. Are we happy with it? Are we actually happy with it? The
Sir,
same thing.
essentially n log n is like an order n, right? The log n term doesn't really contribute that much.
No, it does contribute. What do you mean? N log n is of course much bigger than n. Order
Okay.
n is a small o of n log n.
Okay, right.
Okay. It's not plus, it is multiplied.
Right.
Okay. But this what I'm saying is something not even same. Like say if I toss a coin, toss a unbiased coin 100 times. The expectation is somebody says, oh, my expectation is 50. Of course, expectation of a coin is 50. But are you going to put a bet with me that the coin will not, the number of heads will not be 90?
So could you repeat?
So if I have an unbiased coin, right, and I toss it 100 times, the expected number of heads is 50. Right? But if you say have to kind of put a bet on someone, or if you put a money on something, that what is the value it will come out to be, or something like that, how many number heads will be there? Can you say that the number of heads will not be more than 90?
So with quite a good probability, yes, sir.
Yes. Can you prove it?
Yes, sir. We can just look at the distribution function of the binomial.
Right. So issue is that it is not just the expected value. It is the fact. What is more important for many of us? So it might be that your toss a. So there is two instances that can happen, right? It can for half of the time I get 100 heads, half of the time I get 100 tails. There also the expected value is 50. Right? But that doesn't happen. And basically because we want to say that that distribution of heads is concentrated around the expectation. That's a special property of the distribution. Similarly here, just having a statement that expected value of a randomized quicksort is n log n is not very good for us. I want something like this, that probability that the runtime of a randomized quicksort is more than say 10 log n is very, very low. I want a statement like this. You see that this statement is much stronger than the above statement. Right? This is the concentration stuff. I can not only prove that the expected time is n log n, I would like to prove that not only the expected time is n log n, but for a, in fact, I can make one very, very low also, very, is small o of 1 or 1 by n or something like that. Okay, something which is negligible. Okay, so this is what is called as this concentration of quicksort. So quicksort is an algorithm that not only is on expectation giving us good results, but almost always it is giving us good results. So this is, I am leaving it as an exercise. Is the problem clear?
Yes, sir.
Okay, I'm leaving it as an exercise. Okay, you have to use basically Chernoff bound.
So we have to use what?
Have you seen Chernoff?
Sir,
Hello?
we briefly saw Chernoff bounds in the second semester, but we didn't use them much.
What about Azure?
No, sir, not at all.
So with Chernoff only you can do it. Okay. So this is an application of Chernoff. Think about it. It will also give you the. I don't think that in ISI you do handle this kind of a discrete concentration bound. In computer science, this particular discrete concentration bounds are very, very important.
So could you please just revise this concept of the Chernoff bounds, because
I will give you a link. Okay.
Okay.
I will give you a link. I think the link is already there. This thing of this Baba's notes that I have given you. That is linked in the web page. So there is a very nice work on the concentration results. Okay.
Okay.
So I think this is somewhere the mathematics or statisticians and computer scientists kind of differ a little bit. In the statistical world, it is important to kind of look at this law of large numbers and all of those things. Here, we want something more. We want the rate of convergence. Law of large numbers says that as you take a large n, the number of them is close to reach towards the expectation, right? Yeah, when it says how quickly does it go through the expectation, and that is where we come in, and this is where Chernoff, or even sometimes, so there's this Markov, which is the most simple version, and the Chebyshev, and there's quite a lot of this work that are there. Yeah, the Azumas is basically the kind of the final blow, but if you are not familiar with martingales, and again, you don't have to go into this one. But Chernoff, so I want you guys to go and read this Chernoff bound and try to prove this statement.
So like Chebyshev is using the second moment to bound. Chernoff uses higher moments, right?
So Chebyshev is for general setting. Chernoff is only of a sum of IIDs.
Okay.
Okay, so Chernoff is only for sum of IID. So it's whenever a random variable can be defined as summation of IIDs, where xi's are independent random variables, then you can talk about the concentration of x.
Oh, okay, sir. So then I was mistaken. We haven't done this at all.
We have not done this at all.
I don't think so, sir. I'm not sure though.
But then how are you doing? So the same thing for, like, if you toss a coin, right?
Yes.
You
Sir.
toss a coin n times. So xi guess is xi is equal to head if the I toss is head. There are IIDs samples. The number of heads is exactly equal to x.
Okay.
Right. So expected value of, so if expected value of xi is equals to say p, then expected value of x is p times n.
Right.
What Chernoff will say, the probability that x minus p times, minus, I will not like 2 times n, but minus expected value of x is more than epsilon times n is less than exponential of, or maybe let me write it, it's less than e to the power minus let's not talking about epsilon n as a, okay, minus a squared by n and 3. Because this is the statement. So in the case of coin toss, okay, so this p is half, so this is half, right? So probability that x deviates from n by 2 by some a is less than this quantity. Now put a to be equal to square root n. This quantity is very low, right? So e to the power square root n square is n, so n will cancel out. So e to the power minus half. So put it was 2n or something. So what you will end up proving is that probability that the number of heads in an unbiased coin toss is not between n by 2 minus square root n and n by 2 plus square root n. This is lower than, okay, e to the power minus half. Now, in fact, you can make if you instead of n, if you take 2 or something, you can even push it down. It will be 4 by, I mean, you can make it arbitrarily small that you want. Okay. So from that, you can say that if you are tossing it 100 coins, I can immediately kind of bet that chances that you are going to get more than n by 2 plus square root n, in that case square root n is 10 kind of stuff, so more than 60 or less than 40 is very low. So this is, so you have not even seen this thing at all?
So we've seen this in an exercise.
Okay, so this is something that we need a lot in various ways, and turn-off is, this is only not the only thing. There are various versions of turn-offs and there are lots of things. So if you guys are interested in this kind of probability, I can even point you out to various books and all that kind of, I mean, yeah, because in many times in our field, it is important for us to not understand the expected value, but how close to the expectation is it. And in general, just by using the variance, you will not be able to get something too good a result. But the very fact that if the random variable has some other structure, which usually is of this form, then we can do even better.
So mostly in these kind of cases, we use CLT to give a normal approximation, and then we make confidence intervals.
Right. I mean, CLT will give you something, but the CLTs are still, I mean, because CLTs are done in a slightly more general setting. That's why CLTs cannot harness the extra power of this kind of stuff in general. I mean, if you write a theorem for a very general distribution, then you cannot use some special structure of the distribution, right?
Okay, right.
And
actually, CLT gives us an approximation, and this is an exact bound.
I mean, this is not exact, but it is a tight enough bound.
I mean, sir, there is no statistical implication here. This is just a true statement, but CLT is just using an approximation.
Right, yeah.
Right.
Yeah, I don't think I will have enough scope in this syllabus to go into too much of this thing. But if you guys are interested, I can give you pointers where these things are coming. So if you are interested in this kind of stuff, I think the next course in algorithms will go a bit more into these things when they do talk about randomized algorithms and so on. So this course, I don't think I will be doing any of that. Okay.
You said you would recommend some books about.
So there is this notes of Babai. You can look at it as for the turn-off bounds and all. Notes of Babai that is linked in the web page. Okay.
Yes, sir.
Now, if you are really interested in this kind of stuff, I will really recommend you book for something called a probabilistic method. Now, what is probabilistic method? It's if you want to prove some object exists, right? if you want to prove some particular combinatorial object exists. Yes, when you have various, you have say something like, is there a graph with these structures, some kind of stuff like that, or some objects? How do you prove it? So one way to create a distribution kind of stuff like that, try to generate it with probability, some probability technique, and prove that with some non-zero probability, my graph will satisfy that property. And that will help us to prove that such a structure exists. So that is a very high level picture of it. So a part of it is something of random graph, something that I guess you will do in your next in your master MStat or something. This is the probabilistic technique book by Allen and Spencer. It's a beautiful book. Yeah. So go and read this thing. This is a lot of these connections that are there. Now, this randomized algorithms is of course a very big area. Now you will find these randomized algorithms in various places, but there is this book of Motwani Raghavan. But this might be, you might wait a little bit before you go over this algorithms course properly before you jump into the randomized algorithm. These two, of course, you can jump in right away. And yeah, and right.
Thank you, sir.
Yeah. Okay, so how much time do I have? I have 15 more minutes. So let me ask you, let me change gears completely. Okay, so now this is something. Are you guys tired? Can you just let me know how much tired you are? Because what I'm going to do now will take some serious concentration from you guys.
So before that, can you show the last exercise you gave?
Can I show the last exercise? What do you mean?
I mean the result you just said we have to prove.
Oh. This one.
Thank you, sir.
Okay. So let's see, where are we now? So we started from, maybe if I draw this kind of stuff like that, right? I have time complexity and space complexity. Time, average time, and space. And where were we? Right? So we started with, say, insertion, sort, insertion, bubble, and so on and so forth. Right? And all of them had this to be n square. This was also n square, and this one was order 1. Then we went to merge. The merge sort had this one n log n. Average, of course, went down to n log n, but this went up to order n. Then we had this quicksort, and there the time complexity becomes n square, but the average time complexity becomes n log n, but the space again went down to 1. Right? Now see, one thing you realize that we are getting stuck at n log n. We are unable to break n log n. Why? So the question is that, is there a sorting algorithm that makes less than n log n comparisons? So here I'm assuming that this algorithm, just all it does is that it's taking two entries and comparing. It does not doing anything more funky other than that. And accordingly, they're processing. If you see it, all of them had done so far like that. So it all uses the ordering. Now that ordering, it did not have to have the I mean, give me any element from a total order and it will all work perfectly fine, right? So what do you guys think? Is there an sorting algorithm? So the answer is no. So how do we prove such a thing? So what is an algorithm doing? Let's see. So algorithm is at any point of time. So if I say that this is the starting point, the first thing it does is that it is taking two elements and sampling. Sorry, not sampling, and querying, right? So is this big or this is big? So it is kind of getting only 2-3 answers. So it has some A and B. It is comparing, say, the AI and AJ. And then it is getting either AI is less than AJ or these two are equal or bigger. Now, if it gets that okay, AI is less than AJ, then it can make another some decision. That, oh, now therefore I want to compare I with K. If it is equal, then I want to compare. I can say that oh, I have to compare then J and L. If it's bigger, it can say that J and K, something like that. Right? So at any point of time, it is saying that I am going to make some solve. Again, it has 3 answers. Less than, equal to, greater than. Right. So this is called a tree, I mean, computation tree that is getting formed at any point of time. So I mean, basically, if I just take have another bound here. So basically, this one will say that okay, I have made this first one, I made this one less than, then I got an equality, and then I've got a greater than. Right, and accordingly, I'm making a decision, and I compute. Right, fine.
Yes, sir.
Now at the end of the day, it is output. It is coming to a leaf, and at that time, the algorithm kind of says, "Ah, see, I'm done. There's nothing more to be done. I've got it." Meaning, I can now produce you the actual ordering. So, in some sense, I've given you a sigma, right? That sigma was from Sn. That was the initial ordering that with which I started with. And at the end of the day, the algorithm said, ah, I got sigma. Okay, this is the sigma. Right. Now, it says that it's a sigma. So this is where the computation ends. So this is a computation tree. Is it clear? Any doubt?
So could you just explain what is the notation that you're using?
What is the notation? Which notation?
So the sigma notation.
So okay, so you have been given. So I of course have initially an order, right? A1 is less than A2 is less than AN, right? But
Right.
what you have been given is not this. You have been given A1. I mean, things have been stored in this object in some order. What is the
Right.
order? I have basically permuted this one and put it in, right? So that's the sigma,
Okay.
right? And if you can reorder it back, you know that, okay, this is how I started with, and I have managed and ended up produced a sorted list. So basically, you are ending up learning this sigma.
Okay. Right.
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 I mean, if you have started with the unsorted array and you ended up with sorted array, you basically know this sigma with which it was ordered, right? So
Okay,
output,
right.
I can think of it as a sorted, is basically outputting the sigma.
Okay.
Right? I mean, that's same thing in some sense. Right? You
Right, because sigma inverse is what we're
sigma inverse is what we are computing.
Right.
Right? So this is a computation tree. Now there are two observations that I want you to make. Number one, the number of comparisons. Can you say how many are there? So if this is a run of an algorithm, so maybe some of the branches might end right here. Oh, so this is done. So I've got the answer. This can be sigma 1 or something. Right?
Sir, what is sigma 1?
Some other. So okay, good. Maybe I should ask the second question. Okay. While you are doing it, right? When you started this thing, you had no idea what the sigma was.
Right.
At the end, you're outputting me the sigma. Right? If I had permuted using, say, sigma 1, which is in Sn, you could have done it and output somewhere else, maybe sigma 1. If I started with some other sigma 2, then you would have outputted somewhere here, oh, this is sigma 2.
Sir, I don't understand what you mean by somewhere else. Like what?
Okay. So you have been given an input, right? You are querying,
Right.
you are answering, right? You're going down the tree.
Okay.
And at the end of the tree, you are outputting sigma.
Sir, so we are assuming a finite tree, right? And it has been predetermined what this tree would be. This tree structure is independent of
This tree is
the
the
input.
algorithm's tree.
Okay.
This
Right.
is the algorithm, right? Algorithm is done in some particular way, right?
Okay.
I mean,
Okay.
any algorithm can be thought of as a tree.
Okay. And sir, you're saying that every single leaf of this tree corresponds to some output sigma.
Some output,
sigma
right?
I.
Some sorted array,
Right. Right. Okay.
right? So
Okay.
every leaf of this tree, right? So every leaf is a sorted array, which basically means it is some sigma in Sn.
Right.
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 Okay. So every leaf you are outputting a sorted list. Some
Sorry.
Sir, I have a confusion.
correct.
Sir,
Yeah, go ahead.
sir, that sigma is given. Are we computing? I mean, sorting the array, or we
Sigma
are
is not given to you.
Oh, I mean, we are creating sigma from the sorted array.
I mean, so if I give you an unsorted array, okay, so if I give you aj, say aj, a100, or sorry, a2, a5, a10, a1, a3, a4, and so on, and then at the end you have managed to produce me a1, a2, a3, a10, you have already understood that what is the sigma with which it was permuted.
Yes, so that you told that we learn about sigma. I mean,
Yes,
that's
that means we are
the
learning
sentence.
sigma.
Yes,
Sorting it is learning sigma.
I mean, how to get sigma from the sorted array. I mean, how that was arranged actually.
This is same. Think of it. Okay. If I give you an unsorted array and a sorted array, and I say that, can you give me the sigma? You go and think about it.
Yes, sir, I can do that
Yeah.
from that tree.
From the tree also you can do that, but just directly you can do that.
Yes, sir. Okay, yes.
Okay. I mean, you know that, okay, this A5 is here, A5 has gone here.
Yes, sir.
Right. So you can see the sigma what has going on, or the opposite direction, whatever.
Yes, sir, I understand.
Okay. So outputting the array, a sorted array, is same as outputting the sigma.
Yes, sir.
They two are same, equivalent. Right. So every leaf therefore corresponds to a sigma.
So it doesn't have to be unique, right? We can have two leaves corresponding to the same sigma.
It doesn't have to be unique, but
right.
Every leaf corresponds to at most one sigma.
Right. Right.
That is crucial. Okay. And what is the comparison? What is the worst case runtime? Can you say what is the worst case runtime?
That will be the longest path to some leaf.
Longest path from the root to a leaf, right?
Right.
Okay, good. So here we are. If you are you all fine with it? So I have taken an algorithm, written down this computation tree. Okay. In that case, we have the number of competitors is the now longest path from the root to its leaf. Each leaf corresponds to a sigma in Sn. Right?
Yes, sir.
Okay. Now let's see. Now let's put the whole thing. What is the size of Sn?
Factorial.
So which means that the number of leaves is more than or equal to n factorial.
Yes.
The tree is a 3-array tree. So if the depth, the longest path, is less than d, then the number of leaves is less than 3 to the power d. Right? So d, forget d if you want to make it. So that means that 3 to the power, and this should be number of leaves is less than this, but it has to be more than this. Right?
Yes, sir. Yes, sir.
So where are we?
3 to the
So
power
3 to
d
the
is
power d.
greater than.
So 3 to the power, worst case runtime, say. Worst case runtime is more than n factorial, which means that the worst case runtime is more than log of n factorial base 3. And this you can apply Starling's approximation or whatever stuff, no Starling, yeah, Starling approximation or something. This is omega n log n. Okay, so this is something that I am sure that it will take you some more time to digest. Okay, so I will anyways upload this video today, today's video, and I'll also upload this slides on this notes. Okay, so please go over it, and we'll of course meet again on Thursday. And yeah. This basically shows that any algorithm, worst case runtime cannot be better than n log n. How many of you are confused? Some level at least. None of you are confused? Excellent.
Sir, this algorithm, I mean this runtime, is it for any algorithm or this sorting algorithm?
No, this is a sorting algorithm, of course, because see, the end is like the output things is what is the output, right?
Yes.
The output are n factorial. They are the elements of Sn, right?
Yes.
You can use the same technique for other things. Basically, if at any point of time your action can only produce 3 or a d number of options, and the total number of elements that you have to output is some k, then the depth has to be log of k base d. So we will try to give you some more exercises on this direction. So this is what we call as lower bound. Okay, so this is an example where we can prove that there is a lower bound on the number of comparisons required for sorting algorithm. Now, obtaining lower bounds on algorithms is actually a very hard job. So we don't have too many lower bounds that I can at least present to you in your course. And most of the time, the lower bounds whichever exist becomes very complicated. But this is something that, once again, where, I mean, because we are dealing with theoretical stuff, we really want to get some lower bound. We want to say that, oh, okay, so while we can have a nice upper bound, how far is it from the actual lower bound, that the best? And this is where how we can prove. This is one technique. Okay, there are lots and lots of other techniques for proving lower bound. So we will be giving you some exercises which has some amount of other lower bounds that will come in the picture. Okay. And
Okay, sir.
yeah. So let me stop here today. I've already, I think, exceeded the class hours. Yeah. So I'll see you on Thursday.
Thank you, sir.
Thank you, sir.